Welcome to more OGT math practice. Today we're going to be doing probability problems. First one, it says Renee is selecting a menu for a party. He plans to select a meal that includes one main dish, one vegetable, and one dessert from the following list of choices. So you see his main dishes, the vegetables, and the desserts. How many different meals can Renee select? You could, if you really wanted to, draw a tree diagram for this, where you'd start out with three items, the chicken breast, the salmon, and the beef tips. Then from there, from chicken, then you could have this vegetable, this, or this. Then on top of that, you could have these. But if it's possible to draw a tree diagram, then all we do is we use what we call the fundamental counting principle of probability, which just means if there's three possibilities here, and then you get 4 possibilities here, and you get 5 possibilities here, all you got to do is multiply it. 3 possibilities combined with 4 possibilities with 5. Just multiply those out, and 3 times 4 times 5 is 60 different meals. I think we're going to have another one similar to that. Here we go. Mara packed a blue denim shirt, a red striped shirt, a red plaid shirt, and a black tank top to take on vacation. She also packed 1 pair of denim shorts, 1 pair of white shorts, and 1 pair of beige shorts. She took 2 different pairs of shoes. How many different combinations of outfits? Of course, she's only going to wear 1 shirt, 1 pair of shoes, and 1 pair of shorts at a time. So this is just like the other one. If you look carefully for shirt choices, 1, 2, 3, there were 4 different shirts. There were 1, 2, 3 different shorts, and 2 different pairs of shoes. So all we got to do again is multiply those possibilities together. 4 times 3 times 2, and that should give us 24 different outfits. Here's another one. Just like, I'm hoping you get one on your test because these are pretty easy to do. Casey has one afternoon to run errands involving buying a sweater, mailing a package, and buying groceries. 3 clothing stores around, 2 post offices, and 4 grocery stores within a 10-mile radius. The 10-mile radius is not a number that we're going to be calculating with. They just kind of put that in there because, you know, if you could go forever and keep finding more and more stores. So they're keeping within this area. Choose between these 3 clothings, 2 post offices, and 4 groceries. Once again, all you do is multiply those choices together. 3 times 2 times 4, again, is 24 different choices. Another. One style of jacket comes in 3 sizes, small, medium, or large. They have either buttons or a zipper. They're available in 5 different colors. How many combinations? 3 sizes. Let's say 2 ways to close it, either with buttons or zippers, and it said 5 different colors. So 3 times 2 times 5, 30 different jackets. The stores have to have a lot of space then to put all these different jackets up there. Another one, without the graphic, but it says a banquet offers a choice of 3 different salads, 5 main courses, and 4 desserts. How many different meals? 3 salads, 5 main courses, 4 desserts. 60 choices. Here's another one. This one is the same thing, but it's a little bit more disguised. It says Alfredo has forgotten the 3-digit code to the lock on his suitcase. He remembered that the first digit is 3, and the last digit is either 2 or 4. The middle digit could be any number from 0 to 9 inclusive. What is the greatest number of 3-digit codes Alfredo must have to try in order to be sure to open his suitcase? So he's got a 3-digit code, and he said he knows the first digit is 3. So really we don't have to worry about that. He's going to use a 3. So we don't care. We care about the ones we don't know. It says the last digit's a 2 or 4. So that's 2 choices. The middle digit is anything 0 through 9. Now be careful. 0 through 9 is 10 numbers. You got 1 to 9 plus the 0. So he's got to try 10 times 2 possibilities, which is 20. So he's got to go through 20 different ones, and then he's guaranteed to find his. So it's the same idea. The choices just keep multiplying. Oh, and by the way, if you want to keep this 3 did not represent 3 choices. This represented the number 3 that he knew. So that would be 1 choice if you wanted to use it. One choice would still give you the same answer of 20. Each week, Mrs. Harmona has each of 25 students in her class write his or her name on a piece of paper. All the pieces of paper are put in a jar, and one student's name is drawn from the jar. If Jamie's name was drawn last week, what is the probability that it will be drawn again this week? Okay, now they're trying to trick you a little bit to make it seem more difficult, but it's not. This is each week. It doesn't matter who's won before. Each week, everybody gets their name in. All 25 students get their name in. And so since Jamie's only one out of the 25 students, that's what probability is. Probability is what I call winners over total. Total was 25 students in the class. A winner, in this case, is Jamie, because we're talking about the probability of picking Jamie's name. So Jamie is the only one winner. So that's 1 out of 25. Number 4, Leroy has a number cube with sides labeled 1 through 6. We call that a die or dice for plural, but they don't like to use anything that suggests gambling, so they use the word number cube. But you know that a die, or in this case the number cube, has 1 through 6 on its sides. He tosses the cube 4 times. Each time he gets a 5. What is the likelihood that the next toss will result in 5? Once again, a dice, we assume it's a fair dice because it doesn't say it's not. The probability each toss remains the same, doesn't matter what's happened before. So since there are 6 possible numbers and 5 is only one of those, it's only going to be a 1 out of 6 chance of getting a 5 again. Jack has a box with 10 unlabeled computer CD-ROMs. He didn't label them, but he knows that 2 are music CDs, 3 are games, and 5 are pictures. He randomly selects a CD from the box. Which value represents the probability that the selected CD is music or picture? Okay, remember there's 10 of them. That's our total. Now, a winner. This time we have a couple different kinds of winners, but so we just add them up. A winner would be music or picture. Music, 2, and picture, 5. So our winners, actually, there's 7 winners out of 10. So that's what happens if they use blue and green marbles or whatever, you get to add those together. Okay. Teresa is playing a new board game. She must spin the spinner twice and get the same number both times in order to place her piece on the board. Sometimes it happens you have to roll doubles or spin doubles in order to proceed. The diagram below shows the result of her first spin. So on her first spin, she got a 2. And it says all these have equal chance. You can kind of tell by the way they've divided. They look like equal force of the circle. What's the probability that Teresa's next spin will allow her to move? Well, again, she's got to get a 2. There's 1 spot for 2s out of a total of 4 spots. So it's 1 out of 4 for her to get a 2 on this next spin. Drake School awarded 450 raffle tickets as incentives. The principal will draw 1 winning ticket. The winner will receive a CD player. Drake got 3 tickets for good attendance, 5 for making the honor roll, and 2 for tutoring other students. How nice. What is the probability that one of Drake's tickets will be selected by the principal? Total, 450. The winners are Drake's tickets. He happens to have 3, 5, and 2. So we have to add those up. That adds up to 10 out of 450. And that's not on there. Reason being, sometimes they expect you to simplify probability. Sometimes they do, sometimes they don't. So you could use your ABC button on your calculator if you're not good at reducing this. Some people might see the zeros and say, oh, that's going to be the same as 1 out of 45. Or like I said, you can 10 ABC 450, and the calculator will reduce it for you. Sometimes students just get a tad bit confused the way they present information. It says, here's a table that shows the number of fish caught each day last week, and so on. So Monday they caught 4 fish and didn't catch any on Tuesday. Wednesday 3, Thursday 2, no catches on Friday or Saturday, and got 5 on Sunday. If one day of that week is chosen at random, so you're going to pick from the days, that means you're going to pick out of 7. There's 7 different total days there. Okay, what's the probability that a minimum of 1 fish was caught? So we really don't care how many fish, we just care that some were caught. So winners, Monday's a winner, there was fish caught. Tuesday's a loser. Wednesday's a winner. Thursday's a winner. Friday and Saturday are losers. Sunday's another winner. 1, 2, 3, 4 of the days were winners. 4 out of 7. Okay, now number 19. Now they're starting to get a little harder. Carlos and Tisha empty a bag of 100 colored candies and count the number of each color, and they have it in the chart. Now remember, there were 100, so I don't really have to add those up. They should add up to 100. They return all the candies to the bag and shake the bag. Carlos takes out 5 candies, 2 of which are blue. Then Tisha picks out a candy. What's the probability that Tisha pulls out a blue? So we got to be careful here. There were 100 total, but Carlos removed 5. Let's take 5 off of that total then. And we're talking about probability that Tisha's going to get blue. So there were 15 blue candies. When there were 100 in the bag, there were 15 blue ones. But when Carlos removed his 5, 2 of those were blue. So we're going to subtract those 2 from our 15 as well. So that leaves us with 13 blues out of 95 candies. But they want this turned into a percent. So what you can do is you can divide 13 by 95. 13 divided by 95. And you'll get the decimal of 0.1368. It keeps going. And you can tell what the percent is from that. And if you're not sure, you could take this, you could take 13.68 into the calculator, use the percent key on it, and you will see that it'll give you the decimal 0.1368. Now, if you ABC this, you're just going to get another fraction. You could use the fraction to decimal key to change it, or if you just actually use the divide key, that'll turn that fraction to a decimal as well. Number 39. Rob has 3 red, 4 white, 2 blue, and 5 green t-shirts in his drawer. He picks a red shirt on Monday without looking. Clean and on top. That must be his rule. He notices a stain. He notices a stain on and a stain and I should say sorry. Puts the shirt in the wash. Without looking, Rob then picks another shirt from his drawer. What's the probability he will pick a red shirt on his second try? Some of this got a little bit cut off on his second try. So this reminds me kind of the candies. In the beginning, 3 plus 4 plus 2 plus 5. That makes 14. So he had 14 shirts. But then he took out a red one, which now he has 13 shirts left. But he didn't put that shirt back. He threw it in the wash. So now there were 3 reds, but now there's only 2 reds. That's why we only have 13 shirts. And the probability of red now is 2 out of 13, which is choice A. You don't have to multiply because they were just talking about the probability of picking the red shirt on the second try, not the probability of picking 2 reds, which would have been C. To demonstrate probabilities, a mathematics teacher had students draw marbles from a bag which contained 6 yellows and 14 blues. During class, the bag was dropped, and 2 yellow marbles and 2 blue marbles were lost. In your answer document, tell whether the loss of marbles changes the probability of drawing a blue marble from the bag. If so, was the probability increased or decreased? Support your answer by calculating the probability for each situation. So I did it here. I said before that marbles were dropped, that said that there were 14 blues, but inside the bag were 14 blues and 6 yellows for a total of 20 marbles. So the probability of getting a blue marble before the bag got dropped was 14 out of a total 20. That can simplify to 7/10 or 70%, whichever you prefer. All of these are good probability answers. After the drop, it said 2 blues were lost, so we're taking 2 off our blue total of 14. But we're taking 4 off of our total of 20 because we lost 2 blues and 2 yellows. 4 marbles were lost. So now there's only 16 marbles, and out of those 16, only now 12 are blue. So 12/16 or 3/4, which is 75%. The probability of choosing a blue marble is greater after the bag was dropped. because 75% is greater than 70%. And again, your calculator, you can turn these into a decimal, actually, because sometimes it's hard to tell by looking at the fraction which one's larger. Turn them into a decimal with either by dividing or by using the fraction decimal key. Luca randomly chose a marble from a bag, recorded the color, and replaced the marble before choosing again. The table shows the number of times each color of marble was chosen. So this is like an experiment. Now remember, experiments aren't perfect, so we're able to round off a little bit and do the best we can. It says, according to the data in the table, what is the experimental probability of picking a green? So this is experimental probability because it's not based on exactly what was in the bag necessarily, but on what he had chosen. So we do have to add these up first. If we add up 42, 17, 27, and 14, in the interest of time, I can tell you, that adds up to 100. So there were 100 marbles in the bag. Okay, now, how many times did he pick green? 17. So, green's the winner, 100's the total. So that's his experimental probability, 17 out of 100. Michelle picked a colored cube from a bag of cubes. She recorded the color and returned the cube to the bag. She did this 10 times. The table below shows the color of cube as it was selected. Using the information from the table, how many times would a yellow cube be expected? In 30 picks. Okay, now remember, this is only 10 picks. So this is where you have to start using maybe a proportion to figure out what might happen. So the first thing we're going to do, out of 10 picks, by the way, yellow is our winner. Out of 10 picks, yellow was picked 1, 2, 3, 4 times. So basically, Michelle is very much like Luca. Her experimental probability of picking yellow was 4 out of 10. But we've got to turn this into 30 picks. So we set up a proportion. Instead of 10 total, we want 30 as our total. Then if you're not sure, to solve a proportion, like some people can look at that if they're very good with their facts and say, oh, the answer is 12, because they see that 10 times 3 is 30, so 4 times 3 would be 12. And that's great if you can. If not, all proportions can be solved by cross-multiplying the two numbers that are across from each other. I can't go this way because this is the missing number. So you cross-multiply the two. You can divide by the third. So 4 times 30 divided by 10 is how I can solve this proportion. And that does give me 12. So I would expect 12 yellows out of 30 picks. Here is a two-way, whatever you want to call it, two-way, maybe I don't know if they consider it more than two-way frequency table. So you've got to be careful. They have taken this and separated into males and females, and they also have a total. Then they've also separated by white, non-Hispanics, Hispanics, blacks, and others, and then a total population. So this here is everybody. This is all the women. This is all the men. This is all the others. This is all the white non-Hispanics, all the Hispanics, and all the blacks. So it all depends on what they want to know. And here it is. Based on the data, what is the probability, rounded to the nearest 10,000th, that a male selected at random in Ohio would have been a Hispanic? So they're talking about males being selected. So for our total, we're going to use the male total because they're telling you they're choosing a male. And those are commas. They could possibly look like decimal points too, but those are commas. There were 5,215,573 males. Then it said we want to check the winner is, for this case, is a Hispanic. So we look under the male Hispanic number, which is 76,660. Then the easiest thing to do would be to use the actual divide key on your calculator. 76,660 divided by 5,215,573 573. That'll give you a decimal of 0.014698 and so on. And we're lucky. We really don't have to worry about the rounding because C is the closest to this anyway. And this 6 would round up to a 7 because it's followed by a 9. And so that is answer C. So on these tables, you got to make sure that you're using the column or the row that they're talking about. This, I think, might have been the hardest question in the whole probability section. It says, Annie, Brent, Carl, and Danielle each rolled an identical small wooden cube. Each face of the cube is painted red, yellow, or blue. Now remember, there's 6 sides to a cube, so we don't know how many faces are red, yellow, or blue, but there's got to be at least one of each. The color of the top face is recorded each time the cube is rolled. The table below shows results for 3 of the students after each had rolled the cube varying number of times. And Annie rolled 10 times, Brett went 30, and Carl went 60. So we could just add those up. That is a total of 100 rolls. Okay, in our answer docket, we're going to predict the number of faces on the cube that are red, yellow, and blue. Interesting. Show your work and provide an explanation for how you predicted the number. Then there's another question about Danielle is going to roll the cube 75 times, predict the number of times the cube will land with red on the top face, yellow is the top, and blue. Excuse me. Show your work and provide an explanation. Okay, so what I've done, the first thing, since we're trying to decide how many faces are each color, I have first done what I call the theoretical probabilities. If just one face is a certain color, that's 1 out of 6, rounds off to the decimal 0.17 would be its probability. If 2 of the faces are a certain color, 2 over 6 would be about a 0.33. 3/6 if 3 faces are the same, that would be a 0.5, exactly half. And maybe if 4 of the faces were the same, that would be a 0.67 probability. So that's the theoretical, what you would expect to happen. So what I've done is, first of all, we mentioned it, the total rows was 100. Then I've added up red, yellow, and blue. And I've gotten my reds from this column, my yellows from this column, and my blues from this column. So I don't notice they are in parentheses. So whatever that added up to, I think that was 19. 19 over 100 is 0.19. These, I believe, added up to 45 over 100 is 0.45, and so on. So the experimental probability, remember, they're not going to always be exactly the same as the theoretical. The more rolls you would do, the closer the probabilities would probably get. If you roll it 1,000,000 times, you're going to be pretty close. But we're not too far off, I guess. So I'm trying to look at these numbers and look at these numbers. So what I've decided, I said, I think 0.19 is closest to 0.17. So I predict one face is painted red. 0.45 and 0.36. So I'm going to use 0.45 as 3 faces. It's a little under that. But I guess technically, if you would round that off, 5 rounds up to 4 to a 5. And then for 0.36, I'm going to use 0.33. Then that would work. 1 side being red, 3 sides being yellow, 2 sides being blue, would add up to 6 faces altogether. So those are what I'm going to submit based on my theoretical versus my experimental probabilities. Then it asks me to predict what's going to happen to Danielle. So instead of using the experimental probabilities, I'm going to use my theoretical probabilities now. So if I think there's one red out of 6 would be how many reds out of 75? Or 3 yellows out of 6, how many yellows out of 75? 2 blues out of 6, how many blues out of 75? And remember, cross multiply and divide. So this turns out to be 12 and a half. But you really can't have 12 and a half turn out on rolls. So I said, well, that would be either 12 or 13 reds. And again, the yellows didn't work out perfect either. It was 37 and a half, which means 37 or 38 would be yellow. This one did work out. to be about 25 times we would expect blue. So this was a very, very complicated question, but it was, I believe, worth 4 points. So if we do the math, and it's all about winners, etc. Number 32. This is from 2008. Sometimes it seems like they're getting a little tougher as time went on, because remember, 2009 is the last time we got released number questions. Joel plays tic-tac-toe on his computer. The computer plays first and randomly places an X in one of these grid squares, and they labeled the squares with letters. The frequency table shows the computer's first move for 50 games. So 5 times the computer put its X on A first, 3 times on B, 8 on C, and so on. And if you add these up, they would add up to 50. Based on these results, what is the experimental probability that the computer will place an X in a corner square? Okay, so we check it out. A was 5. C was 8. G was 6. And I was 7. So I would add that up and divide that by 50 times, 50 games. So this is 13, this is 19, that's 26 out of 50. And once again, 26 out of 50 is not on there. But if I were to ABC this, the calculator could simplify it for me, and it does simplify by basically 2 as a factor of the top and the bottom. So 13 out of 25 would be the probability of the computer selecting a corner on its first move. Number 42 here, again, if you think carefully, this turns out to be rather simple, but if not, it can seem kind of enormous. The following numbers are written on individual pieces of paper. 1, 2, 3. There's 5 numbers placed in a bag. Then they pick 4 numbers. 4 numbers are randomly drawn from the bag, and they're placed in the order in which they were drawn to form a 4-digit number. So suppose I pick a 3 first, then I pick a 7, then I pick a 1, then I pick 9. I would have the number 3,719. Okay, now the numbers are not placed back in the bag. It doesn't say that. So once it's drawn, like once you take a 3, you can't get another 3, and so on. In your answer document, determine the probability that a number created in this way has a value greater than 6,000. Show your work and provide an explanation. So if you think about it, all these, he said a 4-digit number, so all these 4-digit numbers, maybe I pick a 7 the first time, then a 6, then a 9, then a 3, et cetera, et cetera. All these are going to be in the thousands. The first number is our clue. The first number tells us whether we're going to be in the 1,000s, the 7,000s, etc. So here's what I've written up. The first pick determines if the number will be less or more than 6,000. Choosing a 1 or 3 would make the numbers in between either 1,000 to 1,999 or between 3,000 and 399. These numbers, of course, are less than 6,000. If you chose a 6, 7, or 9 first, you'd have numbers in the 6,000s or in the 7,000s or in the 9,000s. These are all greater than 6,000. And of course, you can't get an exact 6,000 because there's no zeros in the pick. So as soon as you pick a 6, you get a number in the 6,000 somewhere. So 3 out of 5 choices are winners, making the probability 3 out of 5. If you want a decimal, 0.6 or 60% as the percentage. So that finishes our problem set on probability. Good luck on your OGT. Look for more videos on other topics. Bye for now.